So let's discuss a problem from GATE 2021 physics, and this is from atomic and molecular physics, and it is related to the Raman rotational Raman spectroscopy. And here spacing between the lines would be given, and we need to find next Stokes line appearance. So the problem is as follows. The spacing between two consecutive S-branch lines of the rotational Raman spectra of hydrogen gas is 243.2 per centimeter. So here they have given us spacing between two S-branch lines for which delta J is +2 of the rotational Raman spectra of hydrogen, which is 243.2 per centimeter there, and it has been given in terms of wave number, not in terms of frequency. So wave number is nothing but 1 by lambda. So wave number is 1 by lambda. So meaning of wave number is nothing but number of waves present in 1 centimeter. That means if this is some 1 centimeter, like that, if we think, so how many waves of this wavelength would fit in this 1 centimeter? So that is nothing but the wave number. So in 1 centimeter length, how many waves are present? That is nothing but wave number. So it is decided by the wavelength. More is the wavelength, less is the number of waves, and less is the wavelength, more is the number of waves. After excitation with a laser of wavelength 514.5 nanometers. So here we have we are just throwing laser light on that particular sample which we are studying, Raman spectroscopy, whatever we are studying. So that incident light wavelength is nothing but laser light's wavelength is nothing but 514.5 nanometers. The Stokes line appeared at once 17,611.4 per centimeter for a particular energy level. So after throwing this laser light while observing the Raman spectra, the Stokes line appear at this point. That means in Raman spectroscopy, what we used to do is we used to take a sample and we used to throw light. So what happens is the sample would scatter that light. So if we observe the scattered light, we could observe Stokes and anti-Stokes line. Why means so Stokes lines would be having lesser frequency. So here you can see. So this is when we take a sample and when we throw a light and when we observe the scattered light, it consists of the same as wavelength as the incident light, that is nothing but Rayleigh line, and less than the wavelength of incident light, or means so lesser frequency than the incident wavelength, that means lesser energy, that is nothing but Stokes lines. So this is because of collision of photons with the corresponding atoms in that atoms or compounds present in that particular sample. So if the photon loses its energy in that collision, we would get Stokes line. That only in that process, if photons gain energy, so we would get anti-Stokes lines, which are of higher energy. Higher is the frequency, higher is the energy. Anti-Stokes lines are of higher energy. Stokes lines are of lower energy. So the intensity of Stokes lines is more than that of anti-Stokes line. So it is in Raman spectroscopy, this whatever wavelength we used to take, whether we take 700 nanometers, 800 nanometers, whatever may be, spacing would not change. This spacing between the lines, that is decided by the compound's energy levels of that particular element. So the spacing, everything is because of spacing between the rotational lines. So in general, if we think, so generally there would be electronic energy levels for a compound or atom. If we take a particular compound, particular molecule, so these are electronic energy levels. Same, um, just electronic energy levels we used to find in atoms. So in molecules we used to find this kind of energy levels, electronic spectra. So in between those energy levels we would find vibrational levels. So these are the vibrational energy levels. So again in between them we would find rotational energy levels. So it is the transition between these rotational energy levels that leads to the rotational Raman spectroscopy. So that it is the spacing between these lines that that decides this gap. So if we in whether we are incidenting 600 nanometers or 1000 nanometers, it doesn't matters. So the spacing would remain the same. This is important property of the Raman spectroscopy. And here if we see the next line, the line with lesser frequency, lesser energy next to this original incident line. So in that scattered beam we used to get original incident light, and also some higher wavelengths and lower wavelengths, higher frequencies or lower frequencies. So this is having lesser frequency, lesser energy. So this first line. So the spacing between this Rayleigh and this first Stoke line is nothing but mm, or here it is mentioned it is a 0th Stoke line. So this spacing is 6b, and then from this 0 to first Stoke line the spacing is 4b. So this is the important point we need to keep in mind. So first Stoke line, Rayleigh line, spacing between Rayleigh line and first or 0th Stoke line is 6b. Then that 0th and next consecutive Stoke line is nothing but 4b, and next consecutive line is 4b. That means spacing difference. So if you add 4b 4b like that, we used to get another Stoke lines. In the same manner on the right hand side, for the first anti-Stoke line, the spacing between Rayleigh and the first anti-Stoke line, yeah, or else a 0th Stoke line, here yeah, anti-Stoke line, so it is 6b. Then next line 4b. Then between the next two consecutive lines it is 4b. It continues. Only thing is spacing between this Rayleigh line and this next lines, next first or 0th anti-Stoke or 0th Stoke lines is 6b. Then the spacing changes. So that one we need to keep in mind. So the wave number rounded off to the nearest integer in per centimeter. So they are asking in terms of wave number at which Stokes line will appear for the next higher energy level is. So at next next higher Stokes lines, wave number we need to find out. So here, so what they have given, um, spacing between two consecutive S lines, so S branch lines. So this was given in the question. So here now only we have seen the spacing between two consecutive lines is 4b. 4b, this consecutive lines is 4b only for the Rayleigh and first or only between Rayleigh and next and adjacent Stokes and anti-Stokes line spacing is 6b. For the remaining all it is 4b 4b 4b. It continues. That means if this lines occurs at 6b, this line would occur at 10b. Next line means, so this Stokes lines. So first 6b, next line would be at 10b, next line would be at 14b, and next line would be at 18b. That means the difference between them, this difference between is nothing but gives us so the consecutive difference between those lines is 4b. From here onwards it remains the same. Only between them, between this starting Rayleigh line and this Stoke line, it is 6b. So they have, as they have given us consecutive S branch lines, so the spacing is nothing but 4b, not a, but not a radial line and S branch line like that they haven't given us. So especially it would be called as Q branch line. So but this is S branch line. So here spacing is 4b, and b is equals to, from this what we would get as b is b is equals to 243.2 divided by 4, that is this 60.8. So it is the branch of the line which decides the spacing. So here finally we have got b. So for the S branch lines, delta j is +2. So for Q branch it would be 0. So like that. And O branch it would be -2, like that. So here finally we have got this B. This constant value has 60.8. And next is lambda. Lambda, it was provided in the question, that means we are throwing a laser light of 514.5 nanometers. So in order to observe Raman spectra, first we need to throw an incident light, and we need to observe scattered light. So the light which we are throwing is of wavelength 514.5 nanometers. And here wave number for this, so it is in terms of wavelength. Now we need to find in terms of wave number, because here rotational constant b is also in terms of wave number, like that. So wave number is nothing but simply 1 by lambda, inverse of the wavelength. So 1 by lambda. So 1 nanometer they have given in terms of nanometer. So 1 nanometer is nothing but 1 nanometer is equals to 10 to the power of -9 meters. But here it is in terms of per centimeter. Spacing between the lines they have given provide us in terms of per centimeter. So we need to take 10 to the power of -7 centimeter, because 1 meter is equals to 100 centimeter. So here we can see the wavelength like this. So 10 to the power of -7 centimeter it is. So if we do inverse, we are going to get this. So after multiplication, this 10 to the power of -7 would go up 10 to the power of, it would become 10 to the power of 7, and 1 by 514.5. So we are getting this wave number. That means in 1 centimeter, there would be 19,436 wavelengths nearly. This many waves could be fitted out in that 1 centimeter with the if the wavelength of light used is this. So in that 1 centimeter we can fit these many waves. So that is the meaning of this wave number. So next, so via Stoke's line. So for the Stoke's line wave number they have already given in the question. The Stoke's line appeared at wave number of the Stoke's line. So that one we are considering here. So this is the wave number of the incident light, that is Rayleigh light. Incident light is Rayleigh light is same as the incident light. So this is incident light's wave number, and this is Stokes line's wave number. We need to find a spacing between them, then only we could find out which line it is. Then that means from this diagram it is clear. So here they have provided us this incident beam, that is Rayleigh beam's wave number, and they have given us some line that one could be 7th, 6th, 5th or 4th, 3rd, we don't know. That Stoke line, the number of that particular Stoke line. So what it is we don't know. So but they have given us its wave number. So from that wave number we need to find whether it is 5th or 6th or 7th Stoke line. So this is first, this is second, this is third, this is fourth Stoke lines. Of course it is mentioned 0 here. So we need to find which Stoke line is that. So after finding that only we could know the next Stoke line, next higher Stoke line. So whether if it were a 5th Stoke line, then we need to find 6th Stoke line. If it were a 6th Stoke line, then we need to find 7th Stoke line's wave number, like that. So here, so what we are doing is we are just finding a difference between this Rayleigh line and this Stoke line. So in doing so, that means in subtracting these two terms, what we are getting is 1825. So here this must be equal to this. Y means this is 6b, as we have mentioned, Rayleigh line and first Stoke line, and this is the remaining Stoke lines. That means here, of course, in the diagram it is mentioned as 0, but so this first this distance we need, this distance adds up, and so this is the first Stoke line, and then how many lines after it is are we getting this particular wave number, that one we need to find out. So the spacing overall from here to here, what it would become, some 6b plus number of lines. That means here one, so this is first Stoke line, so 1 2 3 4 5, so here it is 5, so 5 into 4, 4b, like that, because the spacing between next consecutive lines is 4b. So 6b adds up to 4b, next 4b, 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 like that it goes. Hence the simple formula for this is 6b plus n into 4b. So that is first Stoke line, then the spacing between the consecutive Stoke lines. So if we do so, what we are getting is here if this 1825 could be is divided with b, rotational constant, so that we could get the overall spacing. So it is nothing but 30, because this is the difference between Rayleigh line and Stokes line. So the difference, how much difference is that, is 1825. So the difference we are finding in terms of this rotational constant b. So hence we are dividing it with b. So in doing so, we are getting this is nearly equal to 30. So the difference between the Rayleigh line and the Stokes line is 30b. We need to convert it in terms of b. So we have found out that one. So this 1825 has been converted in terms of this b term. So now we are getting finally this equation. So now sending this 6b that side, 30 minus 6 is nothing but 24. So then 4nb is equals to 24b. So bb would get cancelled, for 6 4s are 24. So n is equals to 6. That means it is a 7th Stoke line. That means it is the Rayleigh line. It is the next Stoke line, which is at a distance 6b. Then if we add 4b, that would be 10b. Then 14b. 14b, 18, so this is for, so 6b, it is at 6b, this is 10, 14, 18b, and this is 22b. So 10, 14, 22b, and next it is 26b, and next finally 30b. So here if we see, so this is first, this is second, yeah, so, and this is third, this is fourth, this is fifth, this is sixth, and this is 7th Stoke line. Then next Stoke line is nothing but 8th Stoke line, which would be at 34b. So hence this is the spacing. So from original line to the next highest Stoke line, so from this line to this 8th Stoke line, which we needed to find, the difference is 34b. So that is the thing we needed to find out here. So hence, in order to get the next highest Stoke line, so what we need to do is simply nu minus 34b, because Stokes lines are having lesser wave number. because they are of lesser energy than the original incident light. So the lesser as we go from one stroke line to the another stroke line, it would become lesser. So it would keep on decreasing. Wave number would go on decreasing. So if we want to get anti-stroke line from the Rayleigh line, we just need to add up 6b 4b plus 6b plus 4b plus 4b like that. That only in order to get Stokes line, what we need to do, so the wave number increases in this direction. So here it is shown clearly. So in order to get Stokes line, what we need to do, we need to just subtract 6b 4b 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 like that. So hence from the original line we are subtracting 34b in order to get next higher Stokes line, because this is the seventh Stokes line which they have given us, 30b, the wavelength which they have given in the question. So this Stokes lines, this is the seventh Stokes line. The next Stokes line here is eighth Stokes line which occurs at 34b. So 34 into b is nothing but this. If we multiply b with 34, so we have already got value of b. So this is the value of b. So based on this 60.8, so that 60.8 into 34 if we do, we get this. So if we subtract it from the incident lights wave number, we would get this. If we just round it up, we will get 17,369. So this is the wave number of the next highest Stoke line. And in the key it was given that it could be from, answer could be from 17,367 to 17,371. These are the acceptable answers. So it is 69 is the answer for this question. So this is a solution for this problem. So thank you.